All right, so welcome everybody to today's Mathematics 2 class. Today we'll continue our investigation of differential equation systems and apply the tools that we have developed, namely diagonalization, eigenvalues, eigenvectors, to finally complete our path towards the solution of these systems. Before we do that, a couple of warm-up questions for you. Let's see, I just start those. So the first warm-up question is the following statement true or false? Every polynomial of degree at least 1 has at least one complex root. I'll give you 30 more seconds to answer that. And here's your answers to that question. So most of you said this is true, and of course you're right. After all, that was pretty much the whole point of introducing complex numbers, being able to find roots of all polynomials, no matter how it looks, right? Of course, a constant polynomial other than 0 wouldn't have a root. But if we have degree at least 1, every polynomial has a root, real or complex. And complex includes the real numbers, by the way. Otherwise, I'd say imaginary, purely imaginary. All right, so that's true. Second question, shouldn't be too complex either. Every matrix has at least one eigenvalue, either real or complex. Is that true or false? And I'll give you 20 more seconds to answer that. All right, time's up. So here's your answers to that question. Impressive. Hopefully you noticed that this was basically the same question as before, right? How do you compute the eigenvalues of a matrix? Well, you compute the characteristic polynomial. Basically, that's a determinant of the matrix minus something, and then you're looking for roots of that polynomial. Right? This determinant always yields a polynomial of at least degree 1, because you can start with a 1 by 1 matrix, not less than that. And that polynomial has a root. That root is an eigenvalue. Okay, so the answer is true. Every matrix has at least one eigenvalue. May not be a real eigenvalue, but if you consider complex numbers, every matrix will have an eigenvalue. All right, let's talk about eigenvectors just a little. Third warm-up question. For every n by n matrix, there is a basis of r to the n that consists of eigenvectors of A. Is that true or false in general? Again, I'll give you 20 seconds. That one should be easy. All right. So let's take a look at your answers once again. So here's what you said. Most of you say this is false, and of course you're right again. Basically, that was what we discussed in the last class on Tuesday, criteria for finding out whether a matrix has a basis consisting of eigenvectors or not. Right? You remember this geometric algebraic multiplicity thing? That's basically a way of answering the question. So there are, of course, matrices that don't have a basis consisting of eigenvectors. Otherwise, that whole question would be moot. And final one more question. Let's consider a 3x3 matrix with 3 different eigenvalues. Now, can we guarantee that that matrix has an eigenvector basis? So, more specific situation, is it true then? Again, let's take 20 seconds. And here is the result. Most of you said this is true, and thankfully you're right once again. A 3x3 matrix, that means we need 3 eigenvectors, 3 linearly independent eigenvectors to have an eigenvector basis. We have 3 different eigenvalues, and we have learned that for each eigenvalue there is at least 1 eigenvector, and eigenvectors that belong to different eigenvalues are always linearly independent, right? So 3 different eigenvalues means 3 eigenvectors, and they will be linearly independent because they don't belong to the same eigenvalue. And that means we do have a basis of R3 that consists of eigenvectors of that matrix. So for that specific case, the answer would be true. Right? In general, it might not be true, but in that specific case, it is. All right. So, there's one question that has just been asked on Tweetback. By the way, if you have any questions, feel free to ask, of course, or post your question to Tweetback. The question is, a matrix has eigenvalues only if its determinant equals 0. That is generally not true. Let me quickly give you a rundown of that. So we have a matrix A, right? We want to compute the eigenvalues. What we do is we compute this characteristic polynomial, which is the determinant of A minus lambda times the identity matrix. And we determine the roots of that. Those are the eigenvalues. Right? That means the determinant of A doesn't have to be 0. What we are looking for is the lambdas for which this determinant is 0. What that means is, if the determinant of A happens to be 0, right, then of course that means PA of 0, which is the determinant of A minus 0 times something. That means PA of 0 would be 0. So in other words, 0 is an eigenvalue then. Right? And of course the other direction also holds. If 0 is an eigenvalue, that means it's a root of the characteristic polynomial. Right? So we can go back. And if 0 is a root of the characteristic polynomial, that means this determinant is 0, which is exactly this determinant. Right? So we can go back here as well. So in other words, 0 is an eigenvalue of a matrix if and only if its determinant is 0. Right? But for other eigenvalues, that determinant doesn't tell us a lot. Also, there has been a nice question about geometry. So basically, I'll rephrase the question in a more basic way. At least that's how I understand it. The question is, how can one see this determinant in a geometric way, and how is that related to the eigenvectors and eigenvalues? right? We did discuss the geometry of eigenvectors and eigenvalues. Basically, that means we have this matrix. We regard that as a linear mapping. Eigenvectors are always mapped onto multiples of themselves, right? So the lines spanned by eigenvectors are mapped onto those same lines. So that's why we do this transformation into the eigenvector basis, so that we can say, well, on the coordinate axis, it's easy to understand what that mapping does, right? It stays on that axis and it just shrinks or scales up a point on that axis by some factor, which is the eigenvalue. And one could then ask, well, if I know the determinant of the matrix, is that related to the eigenvectors somehow? You might also remember we briefly discussed a geometric interpretation of the determinant back in the first semester. Basically, the determinant of a matrix is a measure of how much that matrix changes the volume of a body that you put into that mapping, right? So if you take like a square, unit square, for example, and put that into the mapping A, all the points, and you take the result may look something like this, right? That could be a possible result of that mapping. And you'll see, of course, the volume increases, right? And in this case, the volume increases. Basically, the determinant measures the factor of that increase or decrease by a factor of the determinant of A. And to be precise, you'd have to ignore the sign of the determinant for that. Right? So that's what the determinant measures. And how is that related to the eigenvectors and eigenvalues? Well, if you have an eigenvalue and an eigenvector, that tells you, well, this vector is scaled by that factor. So, for example, if you have eigenvalues, all eigenvalues are larger than 1, right? So that means in all the directions given by the eigenvectors, that matrix will just scale up, then you would expect the volume of any body to grow. And that's exactly what happens. So in that case, the determinant would also be larger than 1. The precise connection between those two is the determinant of a matrix is the product of its eigenvalues. Well, we haven't discussed that, so you don't have to know that, but it may be helpful. So the determinant is the product of the eigenvalues, right? That means if we have a large product, if all the eigenvalues are very large, the product will even be larger, and that means what that mapping does is it will grow the volume of any body you put into that mapping by a very large factor. On the other hand, that's something that you can say about the product, but not about individual eigenvalues, right? You might have a very large eigenvalue and a very small eigenvalue, and maybe their product is 1, so that the mapping doesn't change the volume at all, but it might still result in a very different body. Right? For example, you may get something like this here. Maybe in one direction it grows by a large factor, and in one direction it shrinks. So you may get something like this, which possibly has the same value as the original body, but still looks very different. Right? So a determinant of 1 doesn't say the mapping doesn't change the body. It just says, well, the volume is not changing, but it might still be distorted by a lot. And the eigenvalues and the eigenvectors give us a more precise idea of how that distortion works, right? In that case, we have something like a very large eigenvalue in that direction, a pretty small one in that direction, and those would be the eigenvectors. Okay, so that's the relation between the determinant and the eigenvalues. All right, so let's go back to discussing differential equation systems. So you remember what we did is, what we wanted to do is we wanted to solve systems of linear differential equations. To that end, we use this diagonalization approach. Right? So in summary, we had a system like this. Y prime equals a times y. Y is a function that we're looking for, so we need a function that behaves like this. And of course, it's a vectorial function, so it's made up of a couple of functions, y1 to yn, each depending on just one parameter. Usually that's called t for time. Right? So we do have a couple of differential equations that we want these functions to fulfill. And to solve that, what we do is we first try to diagonalize the matrix A. The idea is to decouple the system so that instead of n tightly coupled differential equations that all include all of the functions, we just have one differential equation that includes just one of those functions. Right? And we can solve those individually and then just undo the transformation, put it all back together. So what we want to do is we want to find the basis of Rn that consists of eigenvectors of that matrix A, and we want to find the corresponding transformation matrix S that also consists of those eigenvectors as columns. Then we determine the decoupled system by just executing that transformation. Right? So we compute this diagonal matrix here, where the eigenvalues are on the diagonal. And we use this substitution here to transform our system here into a new system that looks like this. And that's called the decoupled system. Oops. Decoupled. And we can easily solve that. Just solve each line on its own. And once we have that, we use this transformation, the substitution here, to transform our decoupled solution back into the original function space. Right? So that's how we get the solution to the original system. Usually we need to use exponential functions to get the solutions of that system. So of course those exponential functions will also be in there somehow. And maybe we needed to use complex numbers, imaginary units, to achieve that decoupling, right? So the eigenvalues and also the eigenvectors might include imaginary numbers. And in that case, we would then use Euler's formula, like that, to hopefully obtain a solution that works in the real space, right? So we somehow translate the exponential, the imaginary e function, we translate that into cosine and sine parts. I'll show you an example in just a minute to see how that works. And of course there are questions, lots of questions we haven't discussed yet. The two most prominent questions are, what if we cannot diagonalize A? And we do know that might be the case. The answer is there is something that is close to diagonalization that's called the Jordan normal form. That's something like almost diagonal with a couple of ones off diagonal entries. And you can do similar things if you transform into that Jordan normal form, but we will not discuss details here. Just know that it can be done. If the need arises to do that, just ask a mathematician. And the same is true for the second question. That's probably much more important in practice. What if the system is not homogeneous? We didn't discuss that as well. We just discussed that in non-systems, so just one differential equation. What if that appears in systems of differential equations? Also something that's not uncommon in practice, of course. Again, there are methods to deal with this for certain types of inhomogeneities, but that tends to get complicated pretty quickly. So if the need arises to solve something like that, again, don't try this yourself. Ask someone who knows how to deal with those. And probably the system that you're dealing with will be way too complicated to even try an analytic solution. Most systems that are relevant in practice are too large, too complex, too complicated, so they cannot be solved analytically. What you usually do is you try a numerical approach to approximate solutions to these systems. And there's lots and lots of pitfalls in these numerical approaches that you have to know about to make them work. So again, if the need arises for solving such a system, don't try to do this yourself. Ask someone who knows about these pitfalls, right? Otherwise, your rocket might not get to the moon. Actually, there's a pretty high chance it explodes before it even gets off the Earth. Okay, so we won't deal with that in detail. If you want to know more about that, there's lots of great lectures in Garching offered by our department. Feel free to attend. Or just ask someone who knows about those things if you need to solve such a thing. All right, so that's the theory that we'll talk about. Let's talk about an example. You all remember the first example of a differential equation system that we discussed, hopefully. You remember that we discussed an example that involved squirrels and raccoons who compete for resources like food, or space, or water. And so the number of species, the number of animals of one species affects the growth rate of both. And the question that we discussed there was, well, can we solve that, and what does the solution say about the evolution of that ecosystem? And it turns out the squirrels pretty much squeezed out the raccoons. So in other words, all the raccoons died and the squirrels took over. So I'd like to add a different factor, another factor to this now. Basically, to get hold of the mean squirrels, what I'd like to do is I'd like to introduce a predator, somebody that eats squirrels for breakfast. Right? That's always been a very good idea. If you can't control a pest anymore, just introduce a predator and it will all get better. Ask Australia. So that's what we do. In that case, we'll introduce hawks into our system, right? Hawks like to eat squirrels. And for simplicity, let's assume squirrels are the primary food source for our hawks, right? They don't eat anything else. So that also means the growth of the hawk population, of course, depends on the availability of food, which means of squirrels. And also the growth of the squirrel population depends on the number of hawks, right? The more hawks, the less growth for the squirrel population. So let's turn this into an example differential equation system. Let's just say with the growth rate of the hawks, let's call that function h. So h of t is the number of hawks present at time t. The growth rate of the hawks is basically dependent on the number of squirrels available at that time, minus some constant. And we'll assume there's a certain initial hawk species that we'll introduce into the system. So we release 6 hawks at time 0. Number of squirrels at that time is 20, we counted that. And we'll assume the growth of the squirrel population at time t, that depends on the number of hawks, negatively. And we'll also just add a constant to this, right? So not a very complex system, but it should be sufficient to showcase the idea. First thing we need to do is, when we just discussed the topic of inhomogeneities, and of course that is an inhomogeneity, right? A very simple one, it's just constants, not a function. But still, we need to get rid of that first, otherwise our methods won't work. So for that case, there's a pretty simple idea to get rid of those. We just define a new system. So instead of looking at the hawks and the squirrels, we'll look at a function that gets rid of those inhomogeneities by basically subtracting those numbers, right? So we define a new function, y1 of t, that's just the number of hawks minus 10. Right? And if you look at that, so number of hawks minus 10, well, that means this here is basically minus y1. So minus y1 is equal to s prime, or in other words, y1 is equal to minus s prime. Right? So we get that from the second equation here. And we also introduce a function that's basically the number of squares, but we subtract 12. And again, the idea is we want to model this side here, right? Squares minus 12. So h prime is now equal to y2. Right? So our new system is y1 prime is equal to h prime. y2 prime is equal to s prime. And of course, we can express that in terms of y2 and y1 again, and basically we get a system that looks very much like the original one. We get this new system here. Right? If you didn't get that point, just look at that once again in the quiet of your own home. It's not that important for what's going to follow. Just assume this is our original system. And of course, we can also transform the initial values, same way. Okay, so what we want to do now is we want to diagonalize that system. And please note, this is not a decoupled system yet, even though there's just one non-zero entry for these two rows here, but it's the wrong one, right? Decoupled system would mean we have y1 prime here and y1 here, and we don't have y1, but we have y2 here, right? So those are swapped in a way, so that's not decoupled. All right, so we have this matrix, you need to diagonalize this. You might remember we've talked about that matrix before as an example for how to diagonalize the matrix where we need complex eigenvalues. And we computed the eigenvalues already. It turns out it's plus and minus I. And the eigenvectors look like this, one I and one minus I. If you don't remember, just accept that. Right, so we put the eigenvectors into the transformation matrix, and that means this here, this is our diagonal matrix, right? S to the minus 1 AS. We'll have the eigenvalues on the diagonal, so I here, a minus I here, so that looks like this. So now we have that decoupled system. Now we transform our original differential equation system into that decoupled version by using this substitution here. There's a question? Yeah, so I didn't have to compute the inverse of S here actually, because I know if S contains the eigenvectors, then the result of this transformation will be a diagonal matrix that has the eigenvalues on the diagonal. The order matters. The order is the same as the order of the eigenvectors in S, right? So this eigenvector 1i, that's the eigenvector for the eigenvalue I. And this second eigenvector 1 minus I, that's the eigenvector for the eigenvalue minus I. So the order of columns corresponds in S and in D. Otherwise, of course, you can choose any order you want as long as you make it consistent. You'll get the same result. Yeah, you just have different intermediate results, but in the end, you should end up with the same thing. All right, so let's go on. Again, we apply this substitution here. So that means we first need to solve this new decoupled system in terms of the C's. Well, you know how to do that. Well, these are the decoupled differential equations. Notice we have C1 prime and C1 here, so that's just one function, and C2 prime, C2 here, again, just one function, so these can easily be solved. This is the general solution, right? Some constant gamma 1 times e to the it, this is this I here, and some constant gamma 2 times e to the minus it here, this is the minus I that shows up here. And once we have that, we can determine the solution to our original system just by undoing that substitution, basically. We have the C's now, so we can easily compute S times C to get our Y. And once we have the Y, of course, we can get the H and the S back. All right, so this is the S. We just put in our solution here. We keep the constants, and please keep in mind those constants could be different, so don't use the same constant, please. It's one constant for each of the differential equations that we solve in the decoupled system. And that means this is the solution that we get. And now we can use our initial values to compute the correct values for those constants here, right? Gamma 1, gamma 2. We just use the initial values. Remember, those were the initial values for the y's. And that means we can just substitute 0 for our t. And then the result will be this initial value. So what we get is this equation system here. That's a linear equation system for gamma 1 and gamma 2, two equations, two variables. We should be able to solve that. Right, so it's simple Gaussian elimination. If you solve that, here's what you get. So gamma 2 will be minus 2 plus 4i. Gamma 1 will be minus 2 minus 4i. Right, so here's our solutions. And remember, basically, this is the number of hawks and squirrels, plus or minus a constant. Right, so here's how we can compute those. And now, of course, the question you might ask is, what good is that, right? This is some exponential function with an imaginary number in it, and there's imaginary numbers here as well. So how could I ever hope to compute a number of squirrels and of raccoons from something completely imaginary? Right? Probably something like this comes up. I didn't try imaginary raccoons, but they probably look something like that as well. And of course, this is where Euler's formula comes to the rescue. You remember that? E to the it is cosine of t plus I sine of t. And we also have e to the minus it in here, right? So here's it, here's minus it, we need those. Of course, you can use the formula as well for e to the minus it, right? Just use minus t instead of t. The cosine of t, you do remember how the cosine looks, I hope. So cosine, cosine function, that looks something like this. Right, so if I have minus t instead of t, the function value is the same. Right? Cosine function is reflected on the y-axis. That means the cosine of minus t is the same as the cosine of t. For the sine, it's just the other way around. Right? The sine looks like this. So basically, that's not reflected on the axis, but it's reflected on the origin. So the sine of minus t is negative sine of t. So I get this. Right? And now let's take that formula, these two here, and substitute them in place of these e's here and here. Now what we get is a pretty long result, right? So this is our y1. Let's substitute this cosine of t plus I sine of t here, and cosine of t minus I sine of t here. We get this, and then we just try to simplify that a little, and as we do that, you will find that magically all the imaginary things go away, if you do it right. Yeah, you get some I squared here. Remember, I squared is minus 1. Yeah, so this minus times minus turns into a plus, and you'll end up with this function. All right, and that is something that looks more realistic, right? That's a real number again. So it would make sense to say, well, this is the number of squirrels over time, or the number of hawks over time. You do the same thing for y2. Turns out this is what you get. So remember our transformation to get rid of these inhomogeneities in the beginning. You just need to undo that to get to the number of hawks and of squirrels. Right? And here's what you get. So this is the number of hawks over time. This is the number of squirrels over time. And now let's see if we can visualize that briefly. What do I have at here? So let me maybe move that to the side screen. All right. So the online audience can hopefully follow along here. Okay, so I input the functions that we've just computed here. So this is the number of hawks. This is the number of squirrels. Oh, we didn't make a mistake here. And let's try to plot those. And here's what happens. You can see the blue line, this is the number of hawks. Remember that started at 6 and the squirrels started at 20. So the green line is the number of squirrels. And what you can see here is, of course, the number of hawks starts to grow because there's lots of squirrels to feed on. And this growing number of hawks starts to actually feed the squirrels. Right? So what happens is the number of squirrels starts to decline. Right? When the number of hawks grows, the number of squirrels goes into decline. And at some point, there are so few squirrels that the hawks start to get hungry. Right? So in the long term, the population of the hawks doesn't grow anymore. It starts to decline as well. And that, of course, is good news for the squirrels who are not eaten by large numbers anymore. So the number of squirrels starts to increase again. And you can see this cycle repeats again and again. Basically, the number of hawks is a little translate of the number of squirrels, if you want, right? And of course, that kind of reflects the simplicity of our system, right? There were not many other influencing factors in there, and the relations were pretty easy, pretty simple. So that's to be expected. In reality, that might look much more complicated, but the basic idea is the same. You always get a function that fluctuates more or less in the same way if all the other influencing factors are the same, of course. Right? So you can also get functions that look like this as solutions of differential equations or differential equation systems. Even though the solution that you compute is an exponential function, but you can get these sine and cosine functions using the detour over the complex numbers. Right? So the message, in a way, is sine and cosine behave like this, are basically the same thing as the exponential functions if you include complex numbers. So our solution method also works for systems that behave like this. All right, any questions about that? That doesn't seem to be the case. Maybe let's have a brief look. So a brief look at tweetback, see if there are any major questions there. Lots of questions, but none of those is a very good fit right now. Can we get the pictures of the animals in Moodle? Yes, I'll upload the slides. You can have those. All right, so maybe, there's one question I need to answer. This one here. What is the eigenvalue of the zero vector? Would anyone like to take that question? What is the eigenvalue of the zero vector? You should all be able to answer that, actually. 0? Okay. One possible guess. Exactly. So the correct answer, and the only correct answer to a question like this is complete nonsense. The zero vector can never, ever be an eigenvector. If you get that as a result, your computations are wrong. Throw it away, start again. Right? There's no eigenvalue associated to the zero vector. The zero vector is never an eigenvector. So if you find yourself getting that result, don't go on. It would just get worse. Yes. So if you find an eigenvalue and then you compute the eigenvector and the zero vector is the only solution, that means your eigenvalue is wrong. It's not actually an eigenvalue. You did something wrong before that. Yeah, so go back to the beginning, start over. Or maybe better yet, do a different problem first. Yeah, please don't go on with an eigenvector of 0. Eigenvalue of 0 is fine. An eigenvector of 0 is always nonsense. And I hope you will remember that in the exam. I've seen people trying in vain, of course, to invert large matrices with 0 columns in them, getting the most complicated results, and then complaining about those bad numbers. Well, it's your fault. Of course, I didn't get any credits from that point on. All right. So, I'd say maybe take a look at some example problems now, unless there's any more questions from the live audience. And I'll take some of the tweetback questions after the first example. All right. I need to add a date. Today is 2024, April 25th. So I took a few problems from former exams. Here's one that is still in German, unfortunately. Does the audience get that? Yes. I'll try to translate that for you. So that's from a 2016 exam. You have a matrix A, this one here, and the vectors V1 and V2. And now it claims the vectors V1 and V2 are eigenvectors, so the German word is Eigenvektoren. I think that's easy to translate. Of the matrix A with eigenvalues, this is the German word for eigenvalues, lambda 1 and lambda 2. And the question is, determine lambda 1 and lambda 2. Second part of that question, the matrix A has another eigenvector. So this means another eigenvector, lambda 3. And the question is, determine lambda 3 and also determine an eigenvector V3 that belongs to that eigenvalue. And finally, determine an invertible matrix S, invertierbar is invertible matrix S, and a diagonal matrix D with this property. I also think that doesn't need much translation. All right, I hope you all got that. So give that a try and see what you find out. As usual, I have a quick quiz on tweetback asking you for the 3 eigenvalues, lambda 1, lambda 2, lambda 3. quick question to see how your progress is. Who of you is done already? That is very few people, so let's give it a few more minutes then. All right, once again, who of you is done already? A couple more. So let me just take 2 more minutes. All right, I'll give you 20 more seconds to submit your answers, and we'll take a look at the results. All right, so here's the answer for the first question. What is lambda 1? Most of you, well, all of you, said 3 is the answer. 3 is correct. Just review the others briefly. For the second one, most of you said -9 was the right answer, and that is again correct. And for the third one, you also mostly got the correct answer here, which was +9 at this point. Okay, so you mostly got that one right. Just so you know, this is not from one of my exams. That's why this number of points here is a little misleading. If that was my exam, that would probably be something around 14 points, right? Meaning you'd have about 14 to 15 minutes to solve that problem. Yeah, so as a rough guideline, you should be able to finish that in about 15 minutes. Yes? There's a difference because that colleague who did this exam had a total of 20 points for the exam. I usually do a total of 80 points, so basically you have to scale it up by a factor of 4. Yeah, that's it. All right, let's quickly review how to do this. So you have this matrix, you have the vectors already. And you know those are eigenvectors. All you need to do is determine the eigenvalues of those. And of course, what you do in that case is you just compute AV1 and AV2, right, using that matrix and that vector. And what you get is, let's see, if you compute AV1, you'd find the result is 0, 0, 3. Right? V1 is 0, 0, 1. So that is 3 times V1. And you hopefully all remember this eigenvector eigenvalue equation, right? Lambda is an eigenvalue for the eigenvector V if this relation here holds. So in that case, 3 is the eigenvalue for this eigenvector V1. And if you compute AV2, you should find that number is not that nice anymore. The result is this here. So what you get is -9 times V2. And obviously you did that correctly as well. Right, so that's lambda 1 and lambda 2. Okay? Now we have these two eigenvectors and eigenvalues already. In part B, it now says, well, there's a third one. Let's compute that. Unfortunately, there's no great shortcut for that. So if you want to do that, we'll have to take a look at the characteristic polynomial. There is a shortcut, but I won't discuss that. Let's take a look at that. So we need to determine the determinant of, this is the matrix A, 3, 6, 1, and we subtract lambda on the diagonal. Then we have 12 minus 3 minus 1. Again, subtract lambda on the diagonal. And 0, 0, 3. And again, subtract lambda on the diagonal. So here, right? We want to compute the determinant of that. I hope it's obvious how you do that. Just look at that third column here. And you see there's 2 zero entries in there, so it's probably a good idea to use Laplacian expansion with respect to the third column. Right, so that is what we'll do. And that means what we get is this factor 3 minus lambda times the sign. The sign is -1, 2, well, we have the third row and the third column for this entry, so 3 plus 3, times the determinant that we get by deleting this column and this row. So we're left with this 2 by 2 matrix here. Right, so that's the determinant of 3 minus lambda, 12, 6, minus 3 minus lambda. All right. So let's copy that. 3 minus lambda. Minus 1 to the power of 6 is plus 1, so we just leave that out. This determinant here, this is, let's see, 3 minus lambda times minus 3 minus lambda. Let's factor out the minus to make it a little easier. So we write the minus here in front, and then we have 3 plus lambda. And then minus 12 times 6. 12 times 6 is 72, I hope. Yes. All right. Once again, please don't make the mistake of multiplying that in here. We need to factor out these anyway. In the end, you're interested in the roots, right? So ideally, we'll have a product of linear factors. You have this one linear factor here. Just don't touch it. This is nice. Leave it as it is. All right, so we just leave that here. And then in here, let's see, we have 3 minus lambda times 3 plus lambda, binomial formula, right? So that's 3 squared minus lambda squared. And we have this minus here. Oops. This minus here. So it's minus 3 squared, which is 9, plus lambda squared, minus 72. And yeah, this is all very nice. So what we get is lambda squared, and then minus 9 minus 72, this is minus 81. And again, you'll hopefully immediately see this is a binomial formula. Right? 81 is 9 squared, so this is again lambda squared minus 9 squared. So this is, copy the 3 minus lambda, this is lambda minus 9, lambda plus 9. Right? And even if you don't see that, you already know 2 of those roots, right? So you just have to determine the last one. You can do that by either by long division, or of course, if you're there already, you can use the solution formula for quadratic equations. That's both is fine. Yes? So the question is, can you also do Laplacian expansion with rows instead of columns? Yeah, you can. Any row, any column, it always works the same way. Choose one. All right. Okay, so this is what we get. So obviously the roots that we have are 3, 9, and minus 9. We already found 3 and minus 9. So the one that's left is this one here, plus 9. Right, so lambda 3 is plus 9. And then they're also asking for an eigenvector. Again, I'd rather not discuss possible shortcuts. So we're looking for the eigenspace of the matrix A with respect to the eigenvalue 9. That means we're looking for the kernel of A minus 9 times I3. Right? Remember, there's a minus here. So that means, what does it mean? What we get is, let's see, A is this matrix here. Let me just copy that. Or maybe not. Maybe I'll rewrite that. I want the kernel of, let's see, 3, 6, 1, 12 minus 3 minus 1, and 0, 0, 3. And I'm subtracting 9 on the diagonal. Like that. supposed to be a minus 9 here. So I have the kernel of, so 3 minus 9 is minus 6. Copy the other two rows. Then we have minus 3 minus 9 is minus 12. And finally, 3 minus 9 is minus 6. All right, so that's what we get. That means we can simplify this a little by multiplying the first row by 6, adding the first row as it is to the second one, and then adding 1 over 6 times the first row to the last one to get rid of those two factors here. Right, so what we get is then the kernel of, we copy the first row, oh sorry, we don't copy the first row, we multiply by 1 over 6. So that becomes minus 1, 2, 0. If we add the first row to the second row, we get 0, 0, 0, so that vanishes. And for the last row, we add this scaled copy of the first row to this last row. So what we get is, again, 0. And then minus 1 plus 2, that's plus 1, and minus 6. All right, so we're basically done, but just to make it a little nicer, let's swap the last two rows. So this turns into this new matrix here. And that means we have these two pivot elements here. So the last variable is a free one. So what does our solution look like when x3 is free? We use this equation to solve for x2. That says x2 is 6x3. And we use this equation to solve for x1, which says x1 is 2x2, and x2 is 6x3, so that's 2 times 6 is 12x3. All right, so our solution space, and that's the eigenspace we're looking for. Our solution space is then, let's see, x3 is free, so we put a 1 here. X2 is then 6, and x1 is then 12. So that is the eigenspace. Or you could just write this is the span of this basis vector here. Right, so V3, one of the vectors from that span, other than the 0 vector, choose any vector you like. For example, just use that one here. That is one possible eigenvector. And each multiple of that is also fine, of course. All right, questions about this? All right, otherwise let's have a brief look at part C. Remember, part C was, we want that invertible matrix S and the diagonal matrix D such that this holds. So this is a transformation of A to diagonal form, basically. And you know the transformation matrix S that is composed of the eigenvectors. We just use it in the order that we computed them. So V1 was 0, 0, 1. V2 was minus 6, 6, 1. And V3, 12, 6, 1. And then the diagonal matrix corresponding to that, where for V1, the eigenvalue was 3. For V2, the eigenvalue was minus 9, and for V3, the eigenvalue was plus 9. So this is the corresponding diagonal matrix. And remember, this eigenvalue always corresponds to the respective eigenvector in S, right? So if you change the order of the columns of S, you also change the order of the columns of D correspondingly. Otherwise, of course, you can't do that. That's also a completely correct answer. All right, questions? Yes. So the question is basically how long does your answer have to be if this was an exam question? This was an exam question. And in this case, it states explicitly that you don't have to provide any computations or any reasoning, just the results are fine, right? So in this case, the answers could just have been lambda 1 is 3, lambda 2 is -9, lambda 3 is +9, V3 is, whenever V3 is this here, and here's S and D. That would have been sufficient. If I would have asked for a reasoning or computations, then I would expect you to actually carry out these computations as well, right? So at the very minimum, you should write something like AV is this vector, which is 3 times V1, like I did here. And same thing for V2. Yeah, so basically what I wrote here is more or less what I would expect if I were asking for a reasoning or computations. All right. All right, I'm back. Any more questions about that problem? Otherwise, I'd like to answer 2 or 3 from the chat briefly. All right. So someone asked, what is the eigenvalue of a zero matrix? Let's take a brief look at that before we go on. The zero matrix. So we have a matrix, all zeros. I'll just write a 3 by 3 example here. Of course, it can be larger or smaller. And the question is, what are the eigenvalues and possibly also the eigenvectors of that matrix? Does it have any? Of course it has. Which are those, right? So remember, what we need is AV is lambda V, right? Now, if we take any V, like x1, x2, x3, any V here, multiply that with that matrix, what's the result? Well, of course, that's always going to be 0, 0, 0, right? No matter which V we input. So the result is always 0 times our original vector, no matter which vector we use. Well, what does that mean? Well, that means the only eigenvalue this matrix has is 0. Right, so 0 is the only eigenvalue of an all zeros matrix. And of course, that's true no matter what the dimension, the size of the matrix is. And well, what are the eigenvectors? Yes? We have an infinite number of eigenvectors. That is true, but that's always true because we can scale any eigenvector. Yes? Can you be more precise? Which vectors? All vectors? Almost, yes. So the answer is all vectors in Rn, in R3 in this case, are eigenvectors with one exception, and that is the zero vector, right? That is never an eigenvector, not even in this case, right? So what that means is the eigenspace is R3, or Rn in general. The eigenspace does include the zero vector, even though it's not an eigenvector. That's a little tricky. And that means eigenvectors are all vectors in R3 without the zero vector. Please remember to write that if that had been an exam question. All right, so the all zero matrix only has zeros, or it has zero as its sole eigenvalue, and eigenvectors anything but the zero vector. And then a couple people asked for a hint of one of the tutorial problems, so I'll give you a brief hint about those. Specifically, you want to know about E2.5c. Let's see, I have that somewhere. Give me a second to find that. Yeah, so you know what we're talking about. In E2.5, we have this matrix A here. We first determine the eigenvalues and eigenvectors. I'll let you do that by yourself. We find a diagonal matrix and an invertible matrix such that this relation holds, so we diagonalize A. And then the question is, compute A to the 2024. And the question is, how do we do that? And of course, that is related to what we did above, right? You see what we do have here is D is s to the minus 1 AS. And first hint is, if we wanted to compute D to the 2024, how would we do that? Well, D, you know that's a diagonal matrix. There is eigenvalues on the diagonal. It's a 3 by 3 matrix, right? So that should look something like this here. Don't know the actual values, but lambda 1, lambda 2, lambda 3, those are the eigenvalues. So D looks like that. What happens if I compute D squared, D to the third, D to the fourth, and so on? Well, basically that means I multiply D by itself. Yeah? What happens if I do that? Well, let's give that a try. D squared would be this here. So what we get if we compute D squared is, well, take this row times this column for the first entry, so we get lambda 1 squared. For the next row, we take this row, this column, we get 0. For the third row, we get this row and this column, and again we get 0. And of course, that happens for all the rows and columns. You'll only get a non-zero entry if you compute the product of a row with the exact same column here, right? And then you always get that diagonal entry squared. So here you get 0, lambda 2 squared 0, and 0, 0, lambda 3 squared. Right? That means D to the 2024, that's easy. Of course, that same thing happens if you multiply with D once again. So D to the 2024 is just lambda 1 to the 2024 zeros. Then you have lambda 2 to the 2024 zeros. And lambda 3 to the 2024. All right, so it's easy for a diagonal matrix. It's not that easy for a non-diagonal matrix. So we need to apply a little trick here. And that's the following. You can just take that equation and solve for A. Right? Multiply with S on the left and with S to the minus 1 on the right. Remember, left and right does make a difference for matrix multiplication, so be sure to do that correctly. So you get is S times D times S to the minus 1 is A. So A to the 2024 is SD S to the minus 1 to the 2024. Which is the same thing as SD S to the minus 1. minus 1 times SDS to the minus 1 and so on times SDS to the minus 1 and so on 24 times. And I'm pretty sure you can figure out the rest by yourself. I just leave it at that. If that's not sufficient, feel free to ask in the tutorial class in a couple minutes. All right, any more questions right now? Otherwise, I've already shown you the next problem. Maybe let's have a very brief look at that as well. The one question that we can still discuss is that second one. And of course, feel free to try the answer for the first one as well. We have 3 minutes left, so I'll give you 2 minutes to answer that. And as usual, I have a quiz set up about that somewhere here. All right, 1 more minute to answer the question. All right, let's take a look at your answer. So most of you said A can be diagonalized. And of course, most of you hopefully noticed that this is basically a variation of the warm-up question. Right? This is a 3x3 matrix, 3 different eigenvalues. So what does that mean? For each eigenvalue, we have at least 1 eigenvector, 3 different eigenvalues. That means all of these eigenvectors are linearly independent. So there's exactly 1 eigenvector per eigenvalue. All of these are linearly independent. That means they form a basis of R3. So there is a basis of R3 that consists of eigenvectors of A. And that means A can be diagonalized. Okay, so that's the answer. And thankfully in the exam, most people got that right. Okay, so that ends today's lesson. If you have any more questions, feel free to stay for the tutorials. We'll start in a couple minutes. So anything I haven't been able to answer, hopefully our tutors will be able to answer that. Otherwise, I'll see you on Tuesday next week.